We're just going to wait a couple of minutes and then we'll get started. I think we can start. Good morning, everyone, and thanks for joining us today. My name is Gus Ganny. I'm from the Odell HVAC group. Odell is the rep for Cambridge Engineering throughout Ontario and Eastern Canada. Our guests today from Cambridge are Nathan and Jacob that are going to be our presenters. We also have Justin Screamin with us. Justin, I'll let you introduce yourself.
Yeah, thanks, Gus. Hi, everybody. My name is Justin Screamin. I am the regional manager for Canada, Alaska, and 8 United States. I'm located down here in Idaho, so I work with Gus and my team, Jacob and Nathan, on the applications engineering group to basically support you guys. We're going into, I think, probably coming up on going into our 3rd year with Odell. I think we're in our 2nd year right now. And it's been a tremendous experience for both Cambridge and Odell. Odell is one of our largest, if not our largest rep. They do a great job for us, and it's been a pleasure to be able to work with them to bring this Cambridge technology up to the Toronto area. So I just want to welcome everybody and thank you for coming here. I am going to hand this over to Nathan Ocker now, and he is going to lead and then hand it off to Jacob. Thanks, everybody.
Wonderful. Thank you, Justin and Gus, for the intro. Again, my name is Nathan Ocker. I'm the Applications Engineering Manager at Cambridge, and an Applications Engineer, Jacob Wyckoff, is also going to be assisting. So let's get started. Just thank you, attendees, for being here today. Looking forward to spending the next hour or so together. In this session, we'll get a chance to learn a little bit about an exciting technology some may be familiar with, some may not. And if they have not been in the large warehouse industrial spaces, this may be the case. So ultimately, this technology provides a lot of value and offers some unique solutions to our end user engineering clients. So let's jump into the trends. To get us started on this presentation, just wanted to talk about 2 key trends that we're seeing in the HVAC industry. Now, these trends have been prevalent for the last few years and really have become more forefront in the conversations. And so the first trend is ventilation and the need and conversation around it. Traditionally recognized standard for ventilation system design and acceptable indoor air quality is ASHRAE 62.1. And this standard provides procedures, methods for meeting minimum ventilation and indoor air quality requirements for engineers, design professionals, owners, and authorities, where model codes may be adopted. So after past few years, this focus and the need for quality and high performing ventilation systems is really a primary driver for many of the end users and engineers. So that's the first trend. Moving over to trend number two, second trend has been ongoing for many years and has continued as we look into the future of the built environment. And the focus is on energy. How can we not only improve the built environment, indoor air quality, but also lower the energy footprints themselves? I'm sure, as we all know, the commercial building space utilizes quite a bit of our world's energy. And this is because we spend a lot of time inside commercial spaces. And we expect these trends to continue to drive energy efficiency and lower energy usage in all of our commercial spaces. And so as you think about these two key concepts, increased ventilation and lower energy usage, typically those two themes can have somewhat of a tension or conflict. How can they coexist? So at times, end user engineers challenged with that trade-off in order to make buildings safer, in order to have better indoor air quality, and with more ventilation rates. So typically, I'm going to have some sort of energy penalty for increasing ventilation rates. And what I want to talk to you about today is technology that is deployed in spaces where we've been able to increase ventilation rates while also lowering energy footprint. And this would be primarily in these large warehouse and fulfillment center spaces. So as we think about what could that be? We'll jump over to, again, a technology called HTHV, or high temperature heating and ventilation units. For those who have not been in the large warehouse, distribution, or industrial space, could be a new technology to you. That's great. That's a great place to be. A lot of opportunity. So what is HTHV? It's defined by the HVAC industry as 100% outside air, direct fired heater with performance criteria of greater than 140-degree temp rise, and then also greater than 150-degree discharge temp. So those key temp rise and discharge temperatures contribute to making up the HT, the heating portion of HTHV, and then the HV portion, the high ventilation portion, occurs through our fully modulating controls, and that allows us to meet both the ventilation and our space heating requirements. So as you think, in a nutshell, this is the performance criteria for HTHV, and we're going to jump in and talk in depth about how that may impact the sizing, deployment, and ultimately energy efficiency of heating high bay manufacturing, warehouse, and fulfillment centers. So would love to give a little bit of a history lesson, if you'll bear with me, for this technology and the concept of heating buildings with outside air. It's not new, and it has been around for some time. This technology stems back to the mid-90s, where Cambridge introduced this blow-through technology, the high temperature heating ventilation system for design, build, new construction, and mechanical contractors. And what they saw is these large open spaces were primarily being heated with unit heaters or small terminal heating systems. And these were strung along perimeter of the building with large gas connections, maybe numerous gas connections, many pieces of equipment, additional connections, and limited or even no ventilation systems. And what early adopters saw was that they could lower their install cost by over 40% by using larger systems, larger zones, and ultimately greatly reducing the number of installed units, anywhere from maybe 30 to 40 systems down to 6 to 8. And so additionally, end users saw their energy bills cut in half. The benefits of the high temperature heat and ventilation system and pressurization, and really they saw these benefits, that they were not only were they paying less upfront, but they also, the operating costs of these buildings was greatly reduced over time, which is an added benefit. And really the third reason, these buildings generally had no mechanical ventilation before. They primarily met ventilation criteria through a leaky construction of their building, or maybe many operable doors. And so when you look at those three key concepts, those three reasons of lowering install costs, lowering energy bills, and improving indoor air quality through free ventilation, this is what has transformed the warehouse market and continues to be adopted and deployed in many industrial fulfillment centers today. So as we're thinking forward, would like to jump into some education statements as we're thinking about HTHV and trying to take something away today. So I hope you get a chance to walk away with these three key pillars of the inherent design safety of the technology, inherent efficiency of the technology, and also simplicity of design. So as you walk away today, I would like you to have this framework for how the HTHV system delivers multiple technologies in a simple piece of equipment to give more value to our users and installing contractors. For those who may not be familiar with HTHV or even direct fire technology, it might be helpful to do some comparisons of systems as we're thinking about understanding it better. Many of us may be familiar with makeup air, traditional makeup air or draw-through systems. And so these are primarily deployed either in small kitchens or even industrial ventilation systems. Think paint booths or process exhaust. And this technology is 100% outside air. And on the bottom, and we're looking at direct fired combustion system, meaning there's no heat exchanger, there's no flue losses, and this leads to 92% of the thermal energy in the combustion process being delivered to the space. And actually, if you think about the combustion efficiency, it's 100% as there's no wasted energy. That said, the combustion, I guess what I'm saying here is the combustion is delivering all available energy to the space. HTHV is similar in design to the draw-through makeup air, with one key design difference, and this actually impacts performance in a massive way. So HTHV, as you're looking at the diagrams, relocates the blower upstream of the burner, and so that places mechanical devices in the cold air stream. So with that, we can now achieve a performance spec by increasing the discharge temperature, increasing temp rise in order to achieve 160-degree discharge while also in a small form factor. And this is wonderful because we're no longer compromising any of our mechanical equipment, any of our belts, any of our bearings or motors. And so it allows for a higher capacity, smaller volume, and we'll get into more depth about the energy efficiency side, but and maybe even why this is impactful from a low energy footprint. But something that may be on your mind as you're thinking about this technology is, let's first talk about safety. And how is it safe for either this makeup air equipment or even the HTHV technology to deliver all the products of combustion into the space? How is this safe? So as we look forward, when we talk about states with combustion equipment, the core concept is that we want to discuss regarding safety is carbon monoxide. Carbon monoxide, of course, is one of the byproducts of incomplete combustion. And this can lead to unsafe conditions if not properly mitigated. Now, CDC completed a report, and as you see on the screen, with 15,000 emergency room visits and 500 unintentional deaths in the United States caused each year. And so what would the potential causes be as you look forward to the details inside that study? Now, they discovered that the root cause of 2/3 of these CO exposures was situations where automobiles were creating the unsafe environment. And then 1/3 were caused by home heating system, specifically an indirect fired combustion device. And inside that study, they were not able to find a single CO exposure that was caused by a direct fired combustion device. And I find that fascinating that a direct fired system that is designed to deploy and deliver the products of combustion to a space was actually not the cause of any of the CO exposures across the US, though they are widely deployed in many commercial spaces. It begs the question, why? So I'll ask you the question, why? What is the reason that even an indirect fired system, a mechanical system that's designed to separate the products of combustion to the delivered air, was actually the resulting 1/3 of the CO exposures, yet the direct fired 0? So let's look into this root cause. Let's look deeper. What is the single cause for each of these 500 deaths in the US typically each year? Lack of adequate ventilation. Ventilation is the key safety device for any indoor air pollutant, whether it's CO or any other contaminant. So the dose really matters for any of these pollutants. The dose includes the danger. In most cases where we do have CO detection systems, maybe before garages, we see that these CO levels reach an unsafe level. With sophisticated controls, the next step is to increase ventilation, to turn them up, to reduce the levels through spreading out the concentration. And if we think back to the core performance of this technology that we're talking about today, is that these systems are 100% outside air, and they're designed to provide ventilation. There's no way that you can separate the ventilation component from the combustion component of these technologies. They're always together. You will always be ventilating when you're combusting. These products are certified to stringent safety standard listed here, ANSI Z83.4, and that ensures that we have adequate ventilation and low products of combustion, keeping the concentrations low to keep the system safe and allow operation. So when we talk about engineering safety systems, the term ISD, or inherently safe design, can be applied. But the key goals of eliminating some potential severity of consequences, harm, likelihood of occurrence, or potentially even separate people from hazards. Those are the key core concepts to inherently safer design. And these concepts are core to ANSI Z83.4. And they make sure that we do not require engineering controls to make it safe. We aren't just relying on engineering controls, but actually the ventilation component of these devices provides the safety as well. So we will always be ventilating. We can never create an indoor concentration above the discharge concentration of CO. So for those who may be unfamiliar with the safety standard, it certifies that the specifics of it are, it certifies that all products and all of these systems are able to achieve less than 5 parts per million added concentration of CO.
And Nathan,
yeah, go ahead.
If you don't mind, I just wanted to jump in and say that Canada's codes are different than the US, and we fully recognize that. So when Cambridge puts together a Canadian package, we put a specific Canadian controls package that meets all of your CSA requirements up in Canada. There are some additional requirements that we're talking about here in that Z83.4 specific to Canada. So before that becomes a question, yes, we understand the Canadian differences, and absolutely we put in the appropriate controls packages. Just a little Canadian flavor for everybody.
Wonderful. Thank you, Justin. Great point of clarity. So jumping back in at, so if you assume 5 parts per million, just for this exercise, in a worst case, if we have outdoor air at say 7 or 8 or 9 parts per million, you're then adding that 5 parts per million to that incoming air. And so say the outside air is 9, you add 5, you're never going to reach levels above 14. So we'll always be ventilating, always lowering the CO levels inside the space. So we've talked about safety. So that's our safety component of the presentation today. Now let's get into energy efficiency. If you are new to ANSY's 83.4 or direct fired systems or HTHV, your first thought might be, okay, safety, we checked that box. And second thought might be energy efficiency. You know, how can I heat the building with outside air and maintain that energy efficiency? For thinking back to young age, many of us are taught to shut the door or you let the cold air in. Our parents just drill this into us. I know now, especially as I have children, I'm always saying, like, you know, we're not trying to heat the entire world here. We just like to keep our house warm. And so this is just a part of our learned experience from our youth. We want to, and we inherently know we want to lower the outside air requirements to keep it efficient from an energy perspective and cost perspective. So let's look at outside air. As engineers in the ASHRAE world, we know every building must have outside air. We can't completely eliminate outside air from all buildings, and that every building is designed to have human occupancy typically. For those buildings with human occupancy, must bring in outside air and also fresh air. And that's what ASHRAE 62.1 standard does. It gives us a direction and a guideline for how much ventilation buildings might need in order to meet safe indoor air standards. So great. Where from? Secondly, the systems and those buildings must get this air either from natural infiltration or mechanical ventilation. And so many codes have come a long way in terms of maybe the last 5-10 years, making sure we need mechanical ventilation. And very few building standards allow just natural infiltration to meet a requirement now. But ultimately, we know that all buildings need to breathe in some manner to allow that fresh air for the building and the occupants inside the space. And so as we look forward, the final one, from an efficiency perspective, if we look at these large warehouses in high bay spaces, the heating requirement to heat the air from outside conditions is a significant portion of the load. It can be a massive percentage of the overall heat load in a large warehouse or fulfillment center. So let's talk about how is it and what is the most efficient way to heat the air load in these spaces. Let's take an example. Let's look at a large warehouse that has 10,000 CFM outdoor air requirement and say a 0 degree design temperature in order to meet the air load requirements. Yes.
You mind if I jump in a little bit? This is my favorite
absolutely.
slide. I don't know.
Yes.
All right.
Go for it.
Do you mind if I do the next 3? I'm just going to do the next 3.
Perfect.
All right. So let's say that we were going to have an example where we have a building up in Mississauga, and we've got 0 degree Fahrenheit. I'm sorry, I'm going to speak American. 10,000 CFM, 0 degree Fahrenheit air coming in. So this is going to be an interactive part of the presentation. That's why I stole this from him. So if we have 10,000 CFM coming in, 0 degree air, and we raise that temperature 70 degrees, that's pretty simple. I'll give you this one. We have a 70 degree delta T. What does a 70 degree delta T with 10,000 CFM at 0 degrees give us? Gives us 869 MBH of output. Next. And extremely low velocity. So now this is the question that I'd like everybody to think about. Let's say that I designed a warehouse in Mississauga, and the engineer came to Gus and he said, listen, I need to maintain a temperature of 70 degrees in this warehouse. give me a unit. And Gus said, hey, Justin, which one? And I said, this one is 70-degree temporize. Here's the question for the group. How long would this unit run to satisfy that warehouse at 70 degrees? I got to get an answer. Somebody in the chat, somebody jump in and save us. Oh, okay. I got 3 answers coming in. Forever 24/7. All right. Matt Cuomo and Emod, thank you very much. You got it right. So this would run infinitely long. Next slide. So how do you heat the conduction load? You can skip through this one, Nathan. So essentially what that last slide is saying is that we need to keep raising that temperature, and we're going to show you why. So instead, let's say we had that same exact application. We wanted to maintain 70 degrees in Mississauga. We got 0-degree air coming in, right? Let's say instead we crank that temperature up. We're burning gas, right? We're burning it. It's thousands of degrees. How many of those degrees can we steal away from that fire to heat the space? And that really is efficiency. How many of those degrees can we pull away from that heat? So instead, let's say we brought in that 0-degree air, same exact amount of air, 10,000 CFM, but we were able to raise that discharge temperature from 70 to 160. Now we have 160-degree temporize. Next button. Now we have 160-degree discharge temperature, Fahrenheit, which means that we have an additional 90 degrees of heat. And we call that as usable BTUs. So that 90 degrees turns into about 1,118 BTUs. And this is kind of the hardest part to get your head around. It's the difference, right? So that 869 MBH, what that's doing is it's heating the air load. So that's the air that's coming in. So just think we're spending the money for 869 MBH to get that room neutral air. Now, if we actually want to heat the space, what we call that is the conduction load. So the conduction load, the way that I like to frame this is basically it's like the concrete slab that's in the warehouse. It's a giant heat sink. So even if you have 70-degree air coming in, if you have 40-degree Fahrenheit concrete, it's going to be pulling some BTUs out of that air. Again, you're going to have your building envelope, your roof, and your walls are going to be pulling BTUs out of it. So what we're trying to do is we're trying to cram as many BTUs into every one of those CFMs of air as possible, so we end up with the greatest differential. So we are capped by code at 160 degrees, which means we are capped at 10,000 CFM at providing an additional 90 degrees with 1,118 MBH. Next slide. So this chart, and then I'm going to hand it back over to Nathan or Jacob, let them keep going. This chart basically reviews what we just talked about. At the bottom, you'll see if I'm bringing in room neutral air, I have 0 usable BTUs left over to heat the conduction load. And so that is going to run for infinity. As we keep raising that temperature, so let's say we raise the discharge temperature to 100 degrees. Our design temp is still 70. We have 30 degrees left over. That gives us 300 MBH. However, here's the kicker. This is what I really want you to pay attention to. If I only have 300 MBH left over, and I need to heat all that conduction load in that giant concrete floor, I have to shove more air in because every CFM of air has less BTUs in it. So in this case, I have 306 MBH, 39,000 CFM is required to cover that. However, as we keep raising the temperature, you see things get more and more efficient. So at 120 degrees, which is a more typical makeup air discharge temperature, right? Now we have about 500 MBH. Now we're getting reasonable. We can put 24,000 CFM into the space. But here's where that energy efficiency really starts to shine with this HTHV technology, which is different from a lot of our competitors with makeup air. So if you're just charging at 120, 130 degrees, you're going to need roughly 24,000 CFM. So this is the trick. What we do is we then raise it up another 40 degrees. We max it out. When we can discharge at 160 degrees, and the only way to do that, you'll notice in the far left column, is to switch from a draw through to a blow through. Now we get 1,118 MBH left over, which means we only have to put 10,000 CFM into the building. Hit the button, please. So when the 10,000 CFM, one more time, is pushed into the building, we are actually wasting energy, one more time. And when we are wasting energy, that is how we are moving air. So essentially we are paying, and you'll see this on the next slide, for a bigger box, a bigger fan, a bigger motor, a bigger drive system, a bigger everything that's required, including the amp draw to move that. So we are able to heat the building with the bare minimum number of CFM, which then maximizes the efficiency and minimizes the owner's utility bills. Hand it back over to you, Nathan.
Thanks, Justin. All right, so let's talk about the environments we're talking about, high base spaces and stratification that you may see in those cases. You've got 30 to 40 feet of space between the floor and ceiling. And so how are we going to avoid stratification, as this can be just a massive energy impact to a space? You want to keep the heat near occupancy, which would be down near the floor, of course. And then as heat naturally wants to rise, we're going to lose some of that efficiency if we don't address it. So there's many ways to de-stratify a space, of course. Additional technologies, whether it's a HVLS fan, pair fan, zoo fan, to move the air around. Goal is to take the warm air that's going to naturally want to rise to the ceiling and then push it down to occupied floor. So how does HTHV deal with this stratification? What some HTHV technologies typically deploy is what we call high velocity discharge. So through high velocity discharge, we can induce a mixture with large air distribution and large air turnover in a space without having to add additional fans, without having to add additional ducting or even volume of air. Yeah, go ahead, Justin.
Oh, I was just going to ask, are we going to play the animation of this one? If we're not, I would direct everybody to our website or to YouTube. So if you go on our YouTube, Cambridge Air Solutions is what the air tube's on, YouTube's under, excuse me, the air tube. And what it is a 2-minute video, and it essentially walks you through this cycle of how we are mixing the air. And we're not going to run the video probably because this is a presentation over the air, but I'd love for you guys to check out that video. It's about 2 minutes, and it really helps you to understand what it means when we're sweeping the floor, sweeping the ceiling, and we are essentially de-stratifying through high velocity. So check that out on the YouTube channel. Thanks.
Absolutely. Good note, Justin. And really by delivering, as Justin said, the outside air at a high velocity, and utilizing Bernoulli's principle, you can pull the warm, stagnant, stale air at the ceiling. You can pull it into the airstream, and then you're driving that air down with that air coming in the building, and you're inducing a large volume of air. So what HTHV does is it takes, say, from our previous example, 10,000 CFM high velocity air, and through roughly 10-to-1 induction ratio, you're then creating 100,000 CFM of low velocity air mixture. And that can have a tremendous impact in these large open spaces. They can get anywhere from 2 to 5 degrees of temperature variation from wall to wall, floor to ceiling. So that allows for just massive coverage and excellent heat distribution with a single device, one fan, and one ventilation device. So let's move to design considerations. So not every warehouse, as you know, not every distribution center is going to be the same. And so really this is where we must think about how the building's going to be used. So whether there's operable doors, how are they utilizing rack systems, how dense are the rack systems, how is even the storage product being laid out in reference to the heaters. This means we must take into consideration some of these details really to get a good temperature distribution to apply the equipment well. By utilizing some of the key design teams available to you, these systems can be deployed to meet that 2 to 5 degree temperature variation without adding additional air movement devices. With that, Jacob, I'll hand over to you as we continue.
Yeah, thank you, Nathan, for teeing that up for me. Once again, I'm Jacob Wyckoff, Applications Engineer with Cambridge Air Solutions. I'm going to be diving deeper into the efficiency, But first, I'm going to touch on the design flexibility of HTHV. So very important in these retrofit or even new construction applications to have a lot of flexibility to be able to meet the owner's intent with regards to where they want to have these units to be able to have access or make sure they're out of the way, or be able to mount them in the location that's most desirable to get the airflow patterns that we're looking for. So very flexible with through-wall installations, rooftop installations being very common. Also under roof, indoor vertical and outdoor vertical installations being available. So all of these are able to meet the needs of the building and be able to mount these units in a way that meets the owner's needs, and you're able to maximize the amount of usable floor space. So even the largest HTHV unit at 3.2 million BTUs is only going to be about 2,000 pounds, about the size of a larger dining room table. Still very easy to work with and install while still having that huge heat output of up to 3.2 million BTUs. And then the smallest unit being about 250 MBH to be able to meet your smaller building applications. But I'm going to dive a little bit deeper into the efficiency and design impact that Nathan and Justin brought up, and more specifically, how the location of the blower, whether it is a draw-through or blow-through style design, or the location of that blower and the impact that that has on heating a space efficiently using 100% outside air. So we've gone through the reasoning behind the location of the blower and the burner in relation to each other. With the blower and the hot air stream, you're going to have restrictions on your discharge temperature and therefore your delta T, because your belts, your bearings, your motors can only handle temperatures to such high degree before they're going to start to fail. Whereas the blow-through style unit's not going to have that restriction, and you're able to turn up your discharge air all the way up to 160 degrees. So what's the difference, or more importantly, why does this matter? So when we're talking about heating these spaces, we're going to be talking typically about constant volume fans. We've already talked about the differences in discharge temperature, the blow-through unit having the ability to have a higher discharge temperature, where the draw-through unit is going to be restricted anywhere from 110 to 140 degrees. But also, the blow-through unit is going to have that blower in the cold air stream, bringing in that typically roughly 0 degree outside air, that cold, heavy, dense air, whereas the draw-through unit is going to have the air coming off the burner, so it's going to be hotter air that's going to be much less dense. And therefore, the blow-through unit is going to have a much higher mass flow rate per CFM, while the draw-through unit is going to have a much lower mass flow rate per CFM. Now, that's very important because mass flow rate is actually what's going to be the key ingredient in heat transfer, not volumetric flow rate. So if we look at this convective heat transfer formula, this is actually the convective heat transfer formula that governs our industry. And many of us probably haven't worked with this since thermodynamics in college. But the actual formula is total heat transferred equals mass flow of air times the specific heat of air times your delta T. Now, we probably see this or an example like this in metric for some of you. Total heat transferred equals volumetric CFM or fan CFM times 1.08 or whatever correction factor you would use times your delta T. Now, why can't we simply use this formula all the time? Why isn't it 100% accurate? Well, that's because that 1.08 is actually a standard correction factor that's only going to be valid at standard conditions, which is 70 degrees or sea level, or with standard CFM, not with fan CFM. Now, you don't need to worry about the past projects that you design. You don't really need to worry about using the actual convective heat transfer formula going forward. It's just an important distinction because whenever we're comparing and contrasting draw through and blow through, the blowers are seeing such different densities and therefore such different mass flow rates at the fan that it makes a huge difference whenever we're talking about heating efficiently using outside air. So referencing that same formula we had before, you can look at it in the top right, comparing a draw-through versus a blow-through style unit. That draw-through unit, once again, is going to be processing 120 degree air, where the blow-through unit is going to be able to be processing that 0 degree cold, heavy, dense air. That's going to be a large difference in density of 26%, whereas the blow-through unit is seeing 0.086 pounds per feet cubed. The draw-through unit is going to be seeing 0.086 pounds per feet cubed. And that 26% difference in density is going to directly relate to a 26% difference in mass flow, and therefore 26% more BTUs transferred to the space for every CFM processed by that constant volume fan, simply due to the differences in density that the blowers are seeing. Now, we talked about discharge temp previously, going to bring it up one more time because it is very important, and this is a different way to think about it. So looking at the differences in delta T, both units bringing in 0-degree air and discharging for the draw-through unit at 120 and the blow-through unit at 160, that's going to result in a 33% difference in delta T, and therefore it's going to directly relate to 33% more BTUs transferred for every CFM processed by that constant volume fan, simply due to the difference in the ability to increase the discharge temperature. Now, combining those two effects, the 26% higher mass flow rate for the blow-through style unit and the 33% higher discharge temperature for the blow-through unit, adding those two effects together is going to end with 68% more BTUs transferred for every CFM through that unit. Now, remember how Justin and Nathan talked about conductive heat transfer and how that conductive heat load is really what we're designing around in most of these warehousing and distribution applications. That's typically going to be our limiting factors in being able to maintain temperature in the space. So let's talk about the impact that this has on the conduction load specifically. So we talked about conduction load before, where we're turning up our discharge temperature above the space temperature, and every degree that we raise our discharge temperature above the space temperature is what's going to give us BTUs that are usable to cover conduction losses. We call those net BTUs or usable BTUs. So going back to our delta T, the blow-through unit with its higher discharge temperature, except this time looking at the delta T on our difference from space temperature. So the draw-through unit being discharging at 120 degrees, again, using the same example where you have a 70 degree space temperature, is going to have a delta T of discharge temperature minus your space temperature of 50 degrees. Whereas your blow-through unit is going to be discharging at 160 degrees minus your 70 degree space temperature. It's going to be discharging at 90 degrees. Or it's going to have a 90 degree delta T above the space temperature. That results in an 80% difference, which is going to directly relate to 80% more usable or net BTUs transferred for every CFM processed by that constant volume fan. Now, combining those two effects, because we still have our 26% higher mass flow rate, we also have our 80% higher delta T in relation to the conduction load. Combining those two effects gives us a total of 127% more net BTUs transferred for every CFM processed by that constant volume fan. That's going to allow us to use smaller equipment. As Justin said, it's not going to require us to overventilate these spaces. We're going to be able to meet ASHRAE 62.1, but not overventilate these spaces. And it's ultimately going to result in much lower energy usage.
Hey, Jacob, could I say a couple words? So
Sure, yeah.
I would like to jump from this slide just because I slowed us down. It was my fault, to the last couple of slides. So there's 3 slides at the end that are case studies, and I'd like to spend a few minutes talking about those. In the meantime, while Jacob is searching for those, he just passed them. So that is essentially the crux of our approach. We are trying to do this with far less air, and a lot of times there's a demand ventilation or just a standard ventilation ASHRAE calculation. And so what we want to do is we want to look at that first. So we want to look at our ventilation requirements. And then secondly, we want to look at our BTUs. Now, 99 times out of 100, when we look at our BTUs and then we look back at how many CFM it's going to take to move those BTUs, we meet our ventilation calculation. So the majority of the time, unless you're using something else besides a high bay warehouse type application, you're not going to need an additional makeup air unit. This unit will actually function as both the heater, that's its primary function. It will function as the makeup air unit, so it'll introduce the ventilation air, but then it will also do destratification. So it's really taking care of 3 different pieces of equipment. So I love these case studies because it really highlights. So this first one is something we deal with down in the States. I don't think you guys deal with that as much up in the Toronto greater area anymore. I think we've gotten past this, but there are still some states where they love to use unit heaters. So we always like to do a quick comparison of unit heaters versus space heat. So I'll start here. So the way that I want you guys to read these plots, look on the right-hand side on that graph, that black squiggly line, that is the outdoor temperature. So all that's showing you is the outdoor temperature is fluctuating up and down as we're trying to maintain a temperature in the warehouse. So those colored lines, you can see on the top with unit heaters, the colored lines are very spread out. What that means is we have a really big variable between the low temperature and the high temperature within the space. I know these are kind of hard to read, but this is roughly 55 degrees Fahrenheit up to roughly 76 degrees Fahrenheit. So we have a 20-degree F temperature swing, pretty major. If we look at the type of environment that we're able to get, and then we'll talk about the efficiency and what it costs to get this environment with our HTHV heaters, you can see those colored lines are very tightly spaced together now. And what those are thermistors placed all over the building. So what we're able to see is in the coldest part of the building and the hottest part of the building, this is your biggest delta T. And that is what we experience as comfort. That's where the guys that are running between the dock doors and the unit heaters are wearing parkas. We're trying to keep them warm. That's because they may be running through one of those wide color band areas where you have a 20-degree differential. So what we want to do is tighten that up. So as you can see, all those blue and purple lines are all hovering around 65 degrees Fahrenheit. So what that means is this is a more comfortable building for the employees and the occupants to be in. So looking at the middle there, before with unit heaters, we had uneven temperatures, cold dock areas. That's what leads to the uneven temperatures. And in order to achieve that, we were getting no outside air, so we had poor air quality, and we were paying a bunch for gas. So this case study is from 06, 07. We were doing 196,000 therms, and normalized that cost us about 36 cents a square foot. When we were switched over to HTHV space heaters, not only was it more comfortable, but you can compare, we only used 136,000 therms to make the building more comfortable. More importantly, we added outside air, right? That's the big one. And this is a 500,000 square foot building. And so hit the button. We were able to reduce the cost from 36 cents a square foot to 25 cents a square foot, which is pretty significant. About a $60,000 annual energy cost reduction. But this equipment is meant to last for 25 years. So at a bare minimum, from the owner's point of view, I want you to add a zero to that and double it. So we're talking about over $1 million in energy savings over the lifetime of 20 plus years with this unit. Next slide. We're going to go ahead and skip this one just due to the sake of time. Next one. All right, so here's the last one that I would like everybody to take a look at. So this is a direct comparison between draw-through makeup air and blow-through makeup air. And this one is really neat. If you look at the pictures down in the left, you will see that this building looks the same. In fact, it is the same. This is a large distribution warehouse for a really big retailer. I'm not allowed to say who, but they happen to have a bullseye on their logo. So these guys came to us and asked us to design some heating applications, technically the engineer, for their distribution center. They wanted to build 2 different distribution centers, so they saved a few bucks and had both of them engineered at the same time. So these 2 are identical buildings. One is going into Topeka, Kansas. One is going into Columbus, Ohio. Very similar climate. Kansas has about 5,200 heating degree days at 65, whereas Ohio has 5,500. So roughly the same. Gas is $1 a therm. Electric is 8 cents a kW hour. So let's look at how this 1.2 million square foot building performed with 36-foot high walls and the same exact insulation on the roof and walls. And notice that insulation is much lower that they get away with down here in some of the states than we do up in the GMT. We're usually looking at R3040, whereas a lot of times they're getting away with R1925 down here in the States. So in this application, we were able to put in, and this is the way that we designed it, is the top one. We put in 15 of our HTHV space heaters. We mounted them on the roof, and we were able to make that building very comfortable. You'll see the colored lines on both of these are very, very similar to each other. Yes, there's a slight difference in the indoor temperature variation, but for the most part, these are very comfortable. And as an aside, that's not going to be covered in this presentation, but we as Cambridge also offer draw-through makeup air heaters. It's called our M series, but that's not the right application for this, and we're going to show you why. So using these 15 HTHV heaters, we were able to heat this building only using 27,000 MBH. In order to move that 27,000 MBH into the building, we needed to move it using a carrier vehicle of 132,000 CFM. To move 132,000 CFM against the static, we required 95 horsepower. So what that tells us is it costs us about 15 cents a square foot when you encapsulate the gas and electric costs. The same exact building in almost the same exact climate, the same exact number of units, but just switching to draw through with that lower temp heat rise. How did that affect us? Again, same building, same operation. Instead of 27,000 MBH, we use 30,000. Roughly the same, a little bit more with draw through, but the real kicker here is that CFM total. Instead of 132,000 CFM, in order to maintain the same or less comfort, we had to move 210,000 CFM. That's where all your money went. So we needed 150 horsepower with the fan motors, fans, and then not only that, we had to make the actual box bigger itself to keep that same velocity, right? So we needed more sheet metal, a heavier unit. So all said, this is going to cost roughly twice as much to run. And this is why this one is really fun to talk about, because the owner ended up calling us out, and he had gotten a competitor's equipment on that bottom building, and he was very upset because they were having a bigger temperature variation, and he was talking with his counterpart over in Kansas, and they were not having any issues, whereas Ohio was shutting down pretty regularly. So long story short, what we were able to do, and why I love this case study, is we pulled off our competitor's equipment. Even though it was brand new draw through makeup air, and we make brand new equipment like that too, it was the wrong application. And that's, if you don't walk away with anything else today, I want you to walk away with, we need to make sure we have the right application for the right equipment. Draw through makeup air is not a heater, and it's not meant to heat a high bay warehouse. It is meant to make up air. It's meant to replace CFM. A heater, on the other hand, is meant to heat a high bay application, and then you also heat it using CFM, so you get free ventilation. So in summary, at the bottom, the HTHV system used about half the energy of the draw-through system, and they were saving about 177 grand a year. So what did I want you to do? I wanted you to add a zero and double that. So we're talking a couple $1 million in savings over the lifetime of this equipment of 25 years. It's pretty significant impact, and it's really fun to get to go help everybody with their applications, because a lot of folks still don't know this technology exists. So I'm going to hand it back over to Jacob. Thank you.
Yeah, thank you, Justin. And that's going to bring us to just about the end of our presentation, and definitely want to be able to answer any questions that have come up in the chat. Haven't been watching it. I think there was one pending question.
Yeah, we got some questions, Jacob. Let me read them to you.
Sure.
So I think the main one is, does Cambridge offer a CFD analysis to show the destratification effect? And I let Connor know we do have that animation on YouTube, but he wanted to know if we have a computational flow design. Is that what that stands for? Something like that.
Yeah, so we don't offer those CFDs on a project by project basis. I will say that because Cambridge has been doing this for such a long time, we have a very good idea of what it takes to destratify and mix the air within these spaces. So our sales support team will help you with these layouts. We have in our spec manual certain guidance on mounting height above the ground, and then our sales support team can help you with throw distances on distances you can expect to throw the air and avoid stratification and get great air mixing and air movement within your space.
Perfect. Thank you, Jacob. Okay, next question. Real quick, I'll answer this one. What's part of the Canadian controls package? What's the difference? I'm actually going to send this out to Mark Parent at Odell so that he can distribute that. So if anybody else has that question, Mark will distribute that information. Essentially, it's a handful, like maybe 3 extra safety devices that we throw in there, but I'll get exactly what those safety devices are. It's not expensive. It's a few $100s. It's just an additional requirement that we always add to all units going up to Canada. All right, next question. This is a long one, so let me digest here. Okay, are these units designed to be the sole means of heating for the space, or should they be supplemented by unit heaters? Typically, the shell load and ventilation load are not served by the same system as is inherent using only this equipment. I agree this is more efficient for the required ventilation more than a typical makeup air. Buildings don't require outside air at all times. So we are introducing more outside air than we need in this case. So Jacob can, or either one of you, can you handle that? Why are we putting more outside air, and how do we think it's more efficient to cram more air in the building?
Yeah, Justin, I can tackle that one. And that's a great question, Matt. I got a few things to talk about regarding that. So number one is the direct fired efficiency of these units are going to be much more efficient than a unit heater type application. So that's going to make a large impact on there. Along with that high delta T that we discussed further is going to bring on the unit. It's going to heat up the space and it's going to turn the unit off very quickly while bringing in minimal outside air whenever we're unoccupied. And along with that, bringing in that outside air is going to bring the building to a slight positive pressurization, which is going to reduce the infiltration from the building, which is also going to reduce the load within that building. So those three combined typically make our units still much more efficient at heating unoccupied zones than like a unit heater type technology.
Awesome.
I don't know
Thank
if
you,
Nathan or
Jacob.
Justin have anything to add to that.
I would say Matt Cuomo, shoot me an email. I put my email at the top of the thing. Let's discuss this further because this is probably more than like a 2-minute answer. This is kind of the crux of it, and I want to make sure that everybody understands this. So absolutely anybody on this, reach out to Gus, reach out to myself. Let's talk through this and make sure you're super comfortable with it. Because on the surface, you absolutely are right. It doesn't make sense and it's very counterintuitive. And even us engineers have to kind of be taken through the math, and then a light goes off. And I will tell you that when I joined Cambridge 3 years ago, the light had not gone off. I came over from heat pumps. I said, there's no way we're cramming more air into the building and it's more efficient. And I ran through the math and it is accurate. So I would love to talk about this more. This is my main function. Please reach out to me and let's chat. All right, one last one, and it looks like we got a couple minutes left. Given higher efficiency and better performance, is there any rebate for these in Ontario? Gus, can you handle that one if you're still on?
Yeah, I'm on. So that would be something we'd have to reach out to Enbridge and work with them on. We haven't really done that with our with the time we've had Cambridge, but it's definitely something we can get some more information on. At this point, we're just not sure.
So let me add to that. Thank you, Gus. Cambridge Air Solutions actually has an employee. His name is Randy Niederer. He's one of our regional managers. He's been with us for over a decade. He is also kind of our energy ambassador. So what Randy does is he goes to Washington, D.C., he goes to all the state governments, and he works with all of them to make sure that we employ those energy rebates. So he is kind of our liaison that helps get those enacted. He has spoken with Enbridge at length. I believe that he has spoken with Gus and Mike Lett and all the other team at Odell. And what we are working on right now is putting together that rebate package. I'll tell you that I have a rebate package that Randy put together down here in Utah for me many years ago, and it's $6 an MBH. It is a huge rebate program. Now, every place has a different rebate, right? Because they're okay using more gas in Utah probably than we are in the GMT. So we need to look at that. But that is essentially what we would drive towards. That's kind of the pinnacle. If we could get a rebate of about $6 an MBH, and that's US dollars, then I think that we could achieve great things up there. So stay tuned. Let us keep working with Enbridge, with Odell, and we are going to get some of those rebates into place. I assure you of it. All right, we have 1 minute left. Are there any last minute questions? Okay, doesn't sound like it. Well, thank you so much, Jacob. Thank you, Nathan. Thank you, Gus. Thank you, everybody. I think we had something like 73 attendees. This was fantastic. We look forward to touching base with each and every one of you. I put my email at the top of the chat. It's jscreamin@cambridgeair.com. Please feel free to shoot me an email if you have any questions. I'll link you up with our applications engineering group if it's something I can't handle, or we can go to whichever group within Cambridge is necessary. Again, thank you very much for your time and have a great day.
Thanks, Justin. Thanks, Jacob. And Nathan.
Great job, guys. Thank you.
Thank you. Amazing.